Is it recording now? I think it is. Okay. All right. So, you remember back when we were doing area under a curve? Yes? No? Oh, God. And then we found rectangles, yes? And we did like little Riemann sums, which hopefully you still remember how to do. No? You don't know how to do it? Oh, okay. Well, great. So this, we wanted to find the area under the curve, so we took f of x, right? And we multiplied it by this x width, right? And it was f of x times x. And then if we made x infinitely small, and then we added up all the rectangles, then we would have the integral of f of x, and then dx, our delta x, is what we make like super tiny, right? And then we add them all up. Okay, and then we were doing volumes, maybe something that you didn't remember, and maybe we revolved it right here. And so we found the volume of a cross section, which was, we took the integral of the area, right? And then we still made our delta x, our like change in x, right down here, really small, right? And integrate, added them all up together. And so it meant like it's the integral of area times dx, right? Okay, we can't do that in polars. So instead, in polars, we take the area of a sector. So we take one sector and we make like a pie slice out of it. And we find the area of one, and then we add up all of them. So what do we want to make infinitely small in polars? The angle, right? We want the theta to be infinitely small. So let's first start with area of a sector. If I have a full circle, what's the area of a full circle? Okay, pi r squared, right? And then I want a certain portion of the circle, so maybe like this amount of piece, and I tell you like I want 30 degrees of the full circle. Yeah, so you would want to make like, you would want to find out how much of theta, like what percentage of the circle theta makes up. So we take theta and we divide it by, you said 360, but let's go back to radians, so let's do 2 pi. So this will tell me, this part here tells me the percent of the circle, right? Percent of circle. And if I take pi r squared and I multiply it by how much of the percent of the circle I want, then I should get the area of the sector, right? So we simplify it a little bit. Things can cancel. What things can cancel? Yeah, you have a pi on top and a pi on the bottom. The 2 is a 1/2, so we'll bring out the 1/2, and then r squared, and then we have theta. So this is the area of a sector, and that's right here. So that's the explanation of your area of a sector. Are you good with that? Okay, now we want to make them infinitely small, so the theta is what we want to make super small. And if I want to make theta super small, then we end up integrating, and then we add up all the areas of the sector, and that's how you get 1/2 integral from a to b of r squared d theta. So your d theta is what's going to get super small, just like your dx has got super small down here. And then you're just going to integrate r squared. Okay, so this is the formula you need to remember for polars. Polars has a 1/2 in front, shells have a 2 pi in front, discs and washers have a pi in front. area has nothing in front, like area of rectangular has nothing in front. Okay, so remember all those things. Questions? Okay. Here is the formula again for you, if you need it. All right, remember our last unit where you were like, hey, do I need to know these double angles? And I was like, oh, not for this test, but for the next one, probably. Yeah. So remember these two. It's not too hard. Sine squared is 1 minus cosine 2 theta over 2. I remember the sine goes with the one that's a minus, and then cosine squared is 1 plus cosine 2 theta over 2. So the cosine squared is the one with the plus because it's cosine and it's cosine. Okay? All right. Find the area bounded by the graph of r equals 2 plus 2 sine theta. All right, plug in 0. 0 plugged in is, okay, so we go out 2 in this theta direction. And then at pi over 2, sine of pi over 2 is 1. 1 times 2 is 2. 2 plus 2 is 4, so we go up 4. Do you not remember? Pi is 0, 2 plus 0 is 2, and 3 pi over 2 is what? 0, yeah. So this is a cardioid. Make your...
It's an ellipse.
No, it's not an ellipse.
It's a cardioid. Ooh.
Okay. Not bad. Cardioid is if the two numbers are equal, then it's a cardioid. If like, it's on the previous page, like it's on page 89 if you want. But you don't really need, you don't need to memorize all of them. Just like know the general shape that this makes a limaçon, and you're okay. Okay, now we're gonna take small little. So we start and we increase the number of sectors, right? Or slices that we're going to take. And the more we get, the more accurate our area becomes, right? I'm going to keep it at like 50. Now, think about it this way because you're not integrating from left to right now. You're not integrating from up, down to up. You're integrating from 0 and then your angle. So if I integrate from 0 to pi over 2, that's the area that I'm going to calculate. Okay? If I integrate from 0 to pi, what do you think I'm going to calculate?
The other half, too.
The other half, 2, minus the 2 little butt cheeks. Yeah. And then if I integrate from 0 to 3 pi over 2, that would give me one of the butt cheeks. And then I can integrate from 0 to 2 pi. Here's 7 pi over 4, just so you can see. Like it goes down to the angle of 7 pi over 4, but it doesn't, so it's not halfway. You would think it's halfway, but it's not. And then 2 pi is a full circle, right? But some polars complete their full revolution in a period of pi. Some polars complete their full revolution in a period of 2 pi. So you'll have to be careful and know when this completes its revolution. Because if I accidentally thought that this completed its revolution by 4 pi, it would give me double the amount of area that I want. Okay, so let's go back, and then we'll use the formula because we're going to integrate all the way out, all the way, we want the whole thing. The whole thing. So I can integrate from 1/2 integral 0 to 2 pi of 2 plus 2 sine theta squared d theta. Okay. 1/2 r squared theta. Okay. We're going to do the first 3 out, but some of them I'll let you use your calculator for. No, I can't because I don't have a du of cosine on the outside. So I have to expand this. Okay, so that's all multiplied out. And then here's where you're going to need to use the things up here, is because you don't know the integral of sine squared, because you can't do u sub. I would need a cosine on the outside if I was going to do u sub with this sine squared. So we have to go 1/2 integral 0 to 2 pi of 4 plus 8 sine theta plus 4, and then I'll plug in 1 minus cosine 2 theta over 2 in for sine squared.
Wait, why do you have to do that?
Because I can't integrate sine squared, because if I integrate sine theta squared, then I'm going to make u sine, but then I need a du of cosine on the outside, and I don't have it. So I can't do u sub with it. Okay, I'm going to simplify a little bit before I integrate. 4 over 2 is just 2, right? And then you can bring the coefficients out in the front, or you can take 1/2 if it makes it easier and multiply it in, which I'm going to do. So I'm going to make this, 1/2 goes away, I'm going to make this a 2. I'm going to make this a 4. I'm going to make this nothing, right? Okay, now, the integral of 2 is 2 theta. The integral of 4 sine theta is I forgot my negative. And then the integral of 1 is theta. And the integral of negative cosine 2 theta is negative 1/2 sine 2 theta. Okay, plug in 2 pi. So that's 4 pi. Cosine of 2 pi is negative, just minus 4. 2 pi in here is plus 2 pi. And 2 pi in here is sine of 4 pi. That's 0. 0 plugged in is 0 minus 4 plus 0 minus 0. Okay, negative 4, negative 4. This equals 6 pi. Did you get it? Do you need another minute or no? Yeah. Questions? Yeah.
How did you get the integral of 1 minus cosine 2 theta? Can you just go over that? Just that.
Like how to integrate it or where that came from?
Yeah, how to integrate that.
Okay, so like the 4 canceled out with this 2, right? And I made that a 2. But then I multiplied 2 times 1/2 and that canceled out that 2, right? Okay, just look at it on its own. The integral of 1 is theta. That's where this one comes from. Okay, the integral of negative cosine 2 theta, like u is 2 theta. So du is 2, so I have to divide by 2 or multiply by 1/2 in front. Okay, and then the integral of cosine is going to be sine. Yeah. So if you have cosine of 6 theta, then it would be 1/6 cosine 6 theta, right? Or if you have cosine of 4 theta, 1/4 cosine 4 theta. Yeah. The pattern will be easier once you do a few more. Okay, any other questions? All right. Find the area of one petal of r equals 2 sine 3 theta. How do I graph this thing? Why?
So you can wait to wait sine pi over 2. So you just sine this.
Okay, I like what you did there. No, so I'm going to do the same thing, but instead I'm going to plug in plus or minus 2 for r. Which is basically what you did, Junsong. But I'm going to do it like more algebraically. Okay. Why did I set r equal to plus or minus 2? That's where the petal's going to happen, right? My petal's going to be furthest out when my r equals 2, because 2 is my petal length. So if I make my petal length equal to my r, then I'm going to know exactly where my petal is. Yeah? All right, so we divide by 2, so we get plus or minus 1 equals sine of 3 theta. When is sine plus or minus 1? No, not yet. Just 3 theta equals.
Pi over 2.
Pi over 2. When is sine negative 1? 3 pi over 2. And then, so this is where it's positive, right? This is where it's negative 1. And this is, and then give me one more. Because how many petals do I need for this? I need 3 petals, so you might as well find 3 values so you know where all 3 petals are. So 5 pi over 2. And that's also positive, right? Because that will give us a positive 1. Now, if I divide by 3, I'm going to get pi over 6. 3 pi over 6. Oh, might as well just say pi over 2. And 5 pi over 6. Okay. So at pi over 6, which is right here, I'm going to go out my petal length, which is 2. So go out 2 at pi over 6. Okay? And then you come back. Then, something important, at pi over 2, you also go out 2, but it's a negative. So instead of going pi over 2 in this direction, up here, we go down 2. We go the opposite way. So we go down here 2. And then come back. And then at 5 pi over 6, we're positive again, so we go out at 5 pi over 6. Out 2, and then back. Okay, give me my bounded region for one petal.
Wait, which one is 0 to pi?
So you just get the positives and negatives based on what quadrant they fall in?
No, I got the positives and negatives from, okay, sine is 1 at pi over 2. But sine is negative 1 at 3 pi over 2. And then sine is positive 1 again at 5 pi over 2. It's most likely going to go positive, negative, positive if the first number is positive. If this is a negative 2, this would go negative, positive, negative. Okay, give me my bounds. What do you think?
0 to pi.
All right.
For the whole thing.
0. Wait, hold on. What's my equation? 2 sine
Pi over 2, pi over
3 theta. Okay.
One pedal.
0 to 0 to pi is too much. 0 to 0 to pi over 6 gives me that much.
Negative 2 pi. Negative pi over 2, pi over 2.
5 over 3, bro.
Actually, you could find 0 to pi over 6 and then do what? Oh yeah, if I wanted to find, the question says 1 pedal, but if I wanted to find all 6 pedals, then I can multiply by 6. But I just have to, if I could find, for 1 pedal, if I did 0 to pi over 6, I could just multiply that by 2 and then get the other part. Or you can go 0 to pi over 3 and that would give you a full pedal, right? You could also go from pi over 3 to what? That's too much.
Negative 7 pi over 6.
Negative sine.
No. Negative. It's gonna work.
With negative.
2 pi over 3, yeah.
Oh, that's what's up.
Okay. So you can, which way do you want to do it? I like to start at 0. 0 is the easiest. 0 to what?
Pi over 3.
Okay, 0 to pi over 3, fine. I personally would go 0 to pi over 6 and then double it so that the 1/2 is gone, but whatever. You make your own bed.
Make your own bed.
Yeah. Have you ever heard that?
I don't do that.
Oh. You're I believe it.
Oh.
I believe that.
Oh.
Okay, wait, okay, so we square both, right?
Yeah.
4 sine squared 3 theta. I'm gonna pull out the 4
Whoa.
and then I'm gonna replace sine squared 3 theta with 1 minus cosine of what? 6 theta, yeah, because you have to double the angle. The angle's already 3 theta, so you want to double it to get 6 theta over 2. Oh man, I should have just left it. Whatever. These two can cancel, right? Because the formula is 1 minus cosine 2 theta, and since this is already 3 theta, you have to double 3 theta because it's double angle, so it becomes 6 theta. All right.
6 thetas?
Integrate 1.
Theta.
Integrate cosine 6 theta. And 0 and pi over 3.
I am going to.
Okay. So we have 1/6 sine of 6 pi over 3, which is 0. And 0 plugged in is also 0. Oops. Didn't need it. Whatever. Pi over 3. All that for pi over 3.
Wait a minute.
Marcus, your turn. So you do the next example, 4 cosine 2 theta. I'll leave this one up so you can see.
Oh, so 9.
Yeah,
Will I be locked out?
I don't know.
What?
Just leave the door open.
It's pedal, baby. Alright, we gotta do it like that. Alright, so pull it.
Yeah, true.
Forward. How do you know when you're supposed to do like that stuff on the left that we did at first?
You do it all the time.
This stuff?
Yeah.
All the time with pedals.
Yes, all the time with pedals. So this one is 4 cosine 2 theta that has pedals. So you're going to set r equal to plus or minus 4. The ones you don't do it to are the ones that it's like a and b. This is a plus b cosine theta. The ones with the pluses you don't have to, but anytime there's a multiple of a theta, it's probably going to mean that you have a rose.
Okay.
Okay?
Yeah, I need to go over that.
That's why I put them on the previous page, but you'll have practice drawing them on your homework.
Okay.
I decided even if I want rows, I did 0 to pi root 4. So you just do half, right? You know the rows, the half the rows is half the area. The thing is going to be half the
No.
So if I
That doesn't make any sense.
if I know the okay, so if I know it's 2 rows, if there's 2 rows, is 1 is pi root 2, pi root 5. So you do half that.
Oh, wait, yeah, so even double bonds.
Then you do pi root 4, or start with pi root 4, multiply by 2. Or just make it pi root 4.
I think I probably four times. There's the guy.
I like
Oh, so you thought.
You're doing good. You put it negative how much? What is the number? Data.
There's a million ways you can set up your bounds since there's so much symmetry in this.
Your like your limit thing. Also 0.
That's 0 to pi over 2, yeah. Because pi over 2 is down here. Right here? That's 0. So the polar starts like at 0 degrees. This is where the polar starts. Okay. And then at pi over 4, it comes and hits here. At pi over 4, the r is 0. And then at pi over 2, the r is negative 2. Or negative 4, sorry. You could, yeah, because it would still give you two halves of a pedal. Right. Because sine starts at the origin, but cosine starts at the end of a pedal. So there's a difference. You have to know at what location the polar is with respect to like a theta value. Okay, yeah. Yes, so I could go 0 to pi over 4. That would give me half of a pedal and then double it, yeah. There's a million ways you can do it. You just have to be able to visualize.
Did you find this? No, but how do you
Okay, look, do you want to
You know where.
Yeah. So you can focus on, just go with the size of the pedal, so it's like negative 5. Or ultimately, you can go from 0 to pi over 2, or 0 to 0.
Mhm.
Yeah, so you get 2 halves, you get 1 half, and you get 2 halves.
You good, Jonathan? So this is 0 to pi over 4. I could go 0 to pi over 2, and that would get me two halves,
Yeah.
and they would add together to be a whole one. Because right here, your this is at It's very confusing because like polars don't move in a linear direction. So like as your thetas get bigger, your r's don't necessarily always get further away from the y-axis. Yeah, I got 2 pi as well. Not yet. Yeah, thanks. I got 2 pi. What you guys do? Yeah? Yeah. So 0 to pi over 4 will just get you that, but I doubled it.
So for mine, like you have an 8 out in front, but I got a 4.
That's fine.
Is that the way I was saying?
It's going to be fine because when you integrate, like it's going to be cosine of 4 pi over 2.
Oh, and our bounds are
The bounds are different, yeah. Okay. One more minute. Yeah.
how many, or how do you know how many answers you need, like, of, when you have, like,
Oh, for these?
Yeah.
Okay, I always, so even,
Double.
even, yeah, you double. So I need 4 petals, so I'm gonna list 4 answers. Odd ones, you keep the same, because odd, remember this guys, odd number of petals, including circles. Circles are roses with 1 petal. Odd number of petals end their period in 1 pi. But even number of petals end their full period in 2 pi. Which is kind of important because sometimes you'll integrate a circle and you'll go 0 to 2 pi, but it's not. 0 to 2 pi would give you double the amount. But anyways, you needed 3 petals here, so I listed 3 values here. Okay. All right. Any other questions, guys? All right, we're gonna stop doing the integration part by hand because I think you kind of get it. Now we're gonna do areas like of certain sections of a limaçon. So this one says find the area of the inner loop of r equals 1 minus 2 sine theta. Okay, plug in 0 and what do I get? 1. And plug in pi over 2 and what do I get? -1, right? So we go backwards, 1. And plug in pi and what do I get? And then plug in 3 pi over 2 and I get 3. 1, 2, 3. Okay. So you've got 2 parts of your limaçon end up on the same axis, so that's when you know you have a loop. All loops intersect at the origin, so when you start at 0 and you come around, cross at the origin to make your loop and cross at the origin to exit out of your loop. So there's your loop. And then there's the rest of your limaçon. Okay? What am I doing? 1 minus 2 sine t. Okay. So, everybody can see this, right? Okay, I only want the inner loop, which is right here. So how do I know when the inner loop starts and when the inner loop ends? Yeah, it starts and ends when it hits the pole, right? And it's going to hit the pole when r equals 0. So right here I hit the pole, so we're going to set this equal to 0. That's where I'll know where my inner loop and starts and ends. So 1 minus 2 sine theta. So 1/2 equals sine theta. So theta, it starts and ends at pi over 6 and 5 pi over 6, right? Okay. So, this is super easy. If you know those 2 locations, then you can just go 1/2 integral pi over 6, 5 pi over 6 of 1 minus 2 sine theta squared d theta. Right? I could also go pi over 6 to, where do I hit here? That was pi over 2, right? I could go pi over 6 to pi over 2 and double it, right? Okay. So, if I go from pi over 6 to 5 pi, oops, then that gets me a perfect loop inside, right? In my fifth period yesterday, they said pi over 4 to 5 pi over, or 3 pi over 4. But we weren't like zoomed in enough, like we were far out, so they didn't see that it didn't include like extra little pieces, right? So make sure we go pi over 6 to 5 pi over 6. Okay, and then that gets you your loop perfectly. I'm going to do it for you. .5435.
And then the other area is what it's just we're finding the fixed intersection.
I don't know why I'm doing so many decimal places, but whatever. Okay, you'll get the same answer if you do that, or if you do pi over 6 to 5 pi over 6. And multiply it by 1/2. You get the same two answers, right? Okay. All right, cool. So this gets us the area of our inner loop. Yes.
So for inner loops, you just use the two things that you get as your bounds.
Yeah, because that's where it intersects at the origin. So it'll start going into your inner loop at pi over 6, and it will exit out of your inner loop at 5 pi over 6. Okay. What?
Just like the theta's moving and that's your area.
Yeah. So like, I mean, even if you graphed it in polar mode on your calculator, 1 minus 2 sine theta. Okay, if I change my window from pi over 6 to 5 pi over 6, my theta min and my theta max, oops, it'll only graph, whoa. It'll only graph that little inner circle. Okay. Okay. Now, here's a little bit more interesting of a problem. Find the area in between the loops of r equals 1 minus 2 sine theta. So it's the same polar as the other one, but this time I only want like this outside area, not including the loop at all. Okay, so what should I do? Yes, except one small thing, one small issue. Okay. All right, so if I go, let's watch. If I go from 0 to 5 pi over 6, it finds all of that area, right? And then if I go from 0 to pi, it finds this area, and this area, right? And if I go 0 to 3 pi over 2, it'll find this area, and then remember, we're doing area of a sector, so when you make your slices, you can't leave this out. Do you notice how this purple part is double the amount of darkness than this purple part? So this part actually ends up getting overlapped twice. There are, from 0 to 2 pi, there are 2 layers of the circle. There's like one you fanned out and found one small layer, and then you went around again and you calculated double the amount. So it's like 2 pieces of paper on top, and you need to remove both of them. Okay? not too big of a deal. All we do then is we go 1/2 integral 0 to 2 pi of 1 minus 2 sine theta squared d theta. Yeah, and then we subtract the inner loop that we already found in the previous problem. We subtract this inner loop twice. Okay, so 2 times 0.543516. Because there's 2 layers, yeah. Does anybody need me to explain that again? Yes? It's always a double layer, yeah, because when you sweep around, you overlap yourself.
That's why I subtracted.
Yeah, that's why you subtracted twice. So, oh, sorry. Huh? Yeah, you always subtract it twice. Unless I wanted, like, find the area enclosed by it, and you actually want this circle part, then you just subtract it once. Or you could go from 5 pi over 6 to 3 pi over 2. And just double it. Ignore me. Just to do it the way you know. The way you understand. Okay. Are you good? All right, we're not going to calculate this because you can do that on your calculator. 2 more. Now we've got multiple polars. Find the area inside r equals 3 sine theta, which is a what? Circle, yeah, because it's a rose, but it only has 1 petal. So circle out 3, since it's sine, it's going to be out 3 on the y-axis. That circle's not bad. R equals 2 minus sine theta is a, no, limaçon. So, so 0 plugged in is 2. Pi over 2 plugged in is 1. 2 and 3, right? Okay, nice and round. Okay, first thing you want to do is you want to find these intersection points right here and right here where they cross each other, because that's important to know. Okay, so how do I find intersection points? Set them equal to each other. Okay, pi over 6 and 5 pi over 6. Okay. Inside the circle and outside the limaçon means this part, right? Okay, how do you think I find that area? Yes, that's perfect. The area of the circle with these bounds, right? And then subtract the area of the limaçon with the bounds, right? So let's go back to here. What is it? 3 sine t, and What's the other one? Thanks. Where am I going? I'm going from pi over 6 to 5 pi over 6. Okay, so if I find the area of the circle, that gives me all of this area, but it includes this part, because remember, you can't just like not have it. It's area of a sector, so you have to go from the pole out. And then we subtract this part, we subtract that little part down there, and then so if we take this part and we subtract that part, we're just left with this, right? Yeah?
Yup.
Okay, so we just go integral from pi over 6 to 5 pi over 6, put the 1/2 in the front, and then circle whatever's on the outside minus whatever's on the inside. What? Well, if I go from 0 to pi, that's how much area you get. You get too much of this cardioid, I think. Yeah. You get the full circle, too, of the circle, because remember, circles end their period at pi. You get all of the circle, and you get some weirdo section of the cardioid. So it's not. So we got to go by intersection to intersection. Okay? Are you good with that? All right, I'm not going to make you multiply that out. Let's do the last one. Find the area of the common interior of 3 cosine theta. What's that? Circle, diameter of 3. 1 plus cosine theta is a, I don't know. Oh, it's a cardioid, right? 0 plugged in is 2. Pi over 2 plugged in is 1. Pi plugged in is 0. This one's a cardioid. Make it nice and a nice plump cardioid. Plump. Yeah, because you got to be able to see. Okay. Do me a favor and always draw a line from the pole to the intersections of the 2 cardioids. It's going to help you for later.
Wait.
So always, what are you stuck on? The graphing of the cardioids or the drawing the lines out?
Oh, I see.
Okay. Okay, we're almost done. How do I find the intersections of these 2? Set them equal to each other. Pi over 3, and what'd you get? 5 pi over 3. But don't say 5 pi over 3. Say negative pi over 3. I'll tell you why in a minute.
All right.
Are you ready?
Yes.
Okay. Let me draw these. Dang it.
Whoa.
What is... Okay. So if I go pi over 3 to 5 pi over 3, then look what it does. It finds, if I go pi over 3 to 5 pi over 3, it finds this side of the graph, right? So you want to go from negative pi over 3 to pi over 3, so it finds the right side of the graph. It's hard when you're looking backward. This thing doesn't do negatives, so I have to go from 0 to pi over 3. The one problem with this. Okay. So 0 to pi, I'm going to go 0 to pi over 3 and then double it because, so 0 to pi over 3 and then double will get me this area. And then, so I'm going to do it of the cardioid. Right? But then there's a problem because I want the area of the common interior. So if I double it, it would get me from here, like here and here. But there's something missing. These two little small pieces, right, that go with the green graph. So I need to add these two little small pieces on. I call them almond slivers because they look like almond slivers. They do. Have you ever seen an almond sliver?
They do look.
I'll show you. I looked it up before and I was, see, slivered almonds. It looks exactly like that. See? Oh yeah, like a wedge potato. But it's smaller than a wedge potato, so you have to like, because they're great with, they're customer favorite. What? Deborah from West Palm Beach, Florida, and also 55 other people. I'm not going to go further down because maybe you'll see my name. Susan Moy rated them. Susan from Vienna, Virginia, rated them 5 stars. They're great for demonstrating area between two polar graphs. Okay, so we've got to do it. We have to do it of the circle one, right? This one. But I have to change. I've got to start at pi over 3. Okay, so that's where I'm going to start. But then where do I end?
Pi over 2.
How did you get that? Did you just guess?
Intuition.
No, it's like straight up. So it'd be this much, you know.
You're right. But like this is also, pi over 2 is where cosine equals 0. And we want to know where it hits the pole again, right? So pi over 2.
Well, I mean,
Okay, you are right. You're
you can
fine.
look at it in terms of slivers.
So pi over 2. And then I need 2 almonds. So
So just multiply.
we double it, right?
So just
Okay.
know 1.5 in front, baby.
Exactly. I'm going to put it here so you don't forget that it's double it. So we go from pi over 3 to pi over 2. Okay? All right. I posted the website on, as a link on Blackboard, because sometimes I think it's helpful for you guys to see it when you're doing it. So if you want to use the website, this is the first year that I found something that actually demonstrates it kind of nicely. Then feel free to use the website to help you do the homework. Now I'm going to hand back your homeworks, tests, everything back to you, okay?